Greetings, Astronomy 10, and welcome back to your Chapter 9 lecture, or your lecture on the smaller bodies in the solar system, most notably moons and comets, and also the rings around the outer planets, Jupiter, Saturn, Uranus, and Neptune, or the planets in the outer part of the solar system. So to begin with, all of the outer planets have a lot of moons. We only have one, right? Only one major moon. But Jupiter has something like 67 major moons, and Saturn has something like 62. Uranus has something like 27, and Neptune a little over a dozen, something like 14. I'm still congested, I don't know why. In any case, the four largest moons around Jupiter were discovered by Galileo Galilei, and so we call them the Galilean moons. The first of which, the largest of which, is called Ganymede. And one of the sort of subtitles of today's lecture is going to be a short study in why Greek mythology is so messed up. We've taken a lot of names for these objects from Greek mythology. Like Ganymede. Ganymede was the name of Zeus's cupbearer, who Zeus abducted. He turned into an eagle, I think, and abducted Ganymede. Now, Ganymede has a surface that is not completely covered in craters, not quite like our moon is. Thus, it must have been volcanically active until about probably 2 or 3 billion years ago. And if you remember how we determined the age of regions of the surface of the moon by crater density, we can kind of get an idea of how that age was determined. So Ganymede is actually the largest moon of the solar system. It's actually larger than the planet Mercury. It's real big. And so it's the easiest to see. Actually, it's not easy to see. It's a little subtle. But on a clear night, if you look up at Jupiter, you can actually see some of the moons with the naked eye, even on a very clear night. With a telescope, you can see them pretty clearly. They look like independent dots. Trying to see them with a naked eye is much, much more tricky, of course. Europa is much smaller than Ganymede and Callisto. And we've known that there's been water on Europa for a very long time, and so it's sort of significant in that regard. Europa, for a long time, we've known that water was there because of the spectral analysis of the surface. If you look at the light that gets reflected off of Europa, we can see the lines for water, right? And the surface of Europa, of course, is covered in ice because it's very cold out there in that part of the solar system. The ridges that are all over, there's actually a really good picture of it in today's image bank. There are ridges that are kind of all over, crisscrossing the surface of Europa, and that can easily be explained by water below the surface kind of moving around and causing ridge structures to form. Io is similar to our moon, both in size and in mass. But that's kind of where the similarities end, because Io is perhaps the most volcanically active place in our solar system, much more so than even the Earth or the planet Venus. It currently has something like 100 active volcanoes on it, and eruptions there can last quite a very, very long time, because the reason that Io is still volcanically active, even though it's only about the size of the moon, is that it's not volcanically active because of radioactive decay or heating, from things decaying underneath its crust or its lithosphere. Instead, it's volcanically active because there is a sort of cosmic tug of war being played in between Jupiter and the other moons that are kind of pulling against Io and stirring around all of the molten material below the surface. And so after 5 billion years, Io is still volcanically active, uh, mostly because of Europa and Ganymede pulling on it. Now, if we go inward from the edge of the Jupiter's moon system, Callisto, the fourth Galilean moon, is actually first. But the only thing that's remarkable about Callisto is that it's kind of not remarkable at all. It's about the same size as Mercury, but it's not as big as Ganymede. It doesn't have water on it like Europa. It doesn't have volcanoes on it like Io. So it's the boring one, right? It's the boring, sibling that just likes to do homework and doesn't play video games or Dungeons and Dragons with the rest of the family or whatever. I've linked a few videos, and both on today's lecture page and also in the notes. There should be 3. There's one on. There's actually 2 about the Cassini probe, and then one about the Huygens lander landing on the planet Titan. And so these 2 together made the Cassini-Huygens probe vessel. And that mission just ended a few years ago. And that was really significant because not only did we get a really close look at Saturn and its moon systems and its rings, but also the Huygens lander landed on the surface of Saturn's moon Titan. And so there's a video of that. This would probably be a good time to pause this video and go and have a look at those, especially the Huygens landing. That's pretty interesting and pretty exciting. So the place that the Huygens probe landed was Saturn's moon Titan, also named for Greek mythology, right? The Titans, the enemies of the Olympian gods. So Titan has an atmosphere, and it also has lakes, and both of them are made out of hydrocarbons, or compounds that contain both hydrogen and carbon. Hydrocarbon. Pretty simple, right? Things like methane. And the atmosphere is made up of carbon monoxide and other hydrocarbons like methane and ethane and so on. This atmosphere has actually got the greatest amount of atmospheric pressure of any moon in the solar system. It's actually got an atmosphere, got atmospheric pressure greater than Earth's atmospheric pressure, about 1.6 times Earth's atmospheric pressure. And if you watch the video, or if you just look at some of these still images that are in today's image bank, you can see that the surface of Titan, while it appears to be rocky because of sort of the sepia-filtered looking atmospheric haze, right? So when the sunlight comes in, it kind of turns everything like a certain color because of the atmosphere. And all the chunks of rocks and stuff all over the place that look like rocks are actually ice. Water ice. And that's made us hopeful that maybe that there's life there, but we haven't found any evidence so far that there is any life on the moon Titan. It's worth noting also the moon Enceladus around the planet Saturn. There appear to be tons of water and ice there. The surface is frozen, but there's a little bit of sort of outgassing, right? A bunch of water being sort of expelled from underneath the planet's surface out into space through jets. And so we know that there's water there, even though the surface is definitely very frozen. It's small, it's only about 1/10 the size of the moon Titan, but there's definitely water there. The moon Triton, belonging to the Neptune system, is Neptune's largest moon, and it's the coldest moon that we've actually been able to visit. It has a high what we call albedo, and that's a reflectivity, how much light it reflects. And so if we say it has an 80% albedo, that means it reflects 80% of the light that hits its surface. Now what that means for Triton is that it only absorbs about 20% of the sunlight, and so it only absorbs heat from about 20% of the light that actually gets all the way out there to Saturn's orbit, 10 astronomical units from the sun. And so it's very cold, somewhere between 35 and 40 degrees above absolute zero, or 35 to 40 Kelvin. Very cold. That's like minus 230 something degrees C. Very, very cold. By its density, it's probably about 75% rocks and dense refractory materials, and about 25% or so water, mostly water ice, of course. The surface of Triton, while it's sort of peppered by impact craters in some regions, some parts of it seem relatively young. And this could possibly be because water or maybe ammonia freezing and eroding and sort of overriding the surface of Triton. Now, the body out in the outer solar system beyond Neptune is no longer a planet, and if you watched Rick and Morty, you probably know that I'm talking about Pluto, right? The dwarf planet, or the Kuiper Belt object. When Pluto was discovered, it was decided at the time that it was going to be a planet, largely because it was discovered by an American, so it was the American planet. And back then, the world actually used to like us, because we were turning out lots of Nobel Prize winning scientists and actually doing things to help the world. And that was before, we decided to do a bunch of really crappy things and kill people for oil and all this other disgusting stuff. And so, the world likes us less nowadays because we're giant jerks. But when Pluto was discovered, back then, science fiction was sort of a driving force culturally, kind of the world over. And so Percival Lowell had these crazy theories about there being intelligent life on Mars, and having canals on the surface of Mars to sort of irrigate its surface or whatever. These theories were actually really, really popular. But popular opinion really cannot change fact. And when Pluto's moon Charon was discovered, Charon, of course, is the boatman who ferries people across the river Styx into Hades, which, if you ever played Hades, it's excellent. I can highly recommend it. We learned that Pluto was not an Earth-like planet, like scientists and science fiction authors alike had sort of hoped. Of course, it's way, way far out in the outer solar system. It's far too cold for it to support life like us. In any case, around that time it was discovered that Pluto also had a very eccentric orbit, or it's stretched out like an oval, not like a circle, right? Earth's almost like a circle. Earth's orbit is almost like a circle. It has an orbital eccentricity of about 1%. But Pluto's orbit is way eccentric. It's like way, way, way far out. It goes inside Neptune's orbit on one side, on the short side, and then on the other side it goes way, way far out, like almost somewhere between 2 and 3 times as far as Neptune's orbit, I think, on the far end. And so it's a very eccentric orbit, not like the planets. The other planets all have like a stable, not super eccentric orbit, but they don't overlap. Because if you remember, the standard definition of a planet was that you had one body It kind of swept up all the material at one sort of set of distances from the sun, and it becoming the dominant gravitational feature and pulling in all the other materials what made it a planet, right? So not only does Pluto's orbit really eccentric and cross inside Neptune's orbit, its orbit is also tilted compared to the plane that all of the other planets orbit around the sun. In the 1990s, we learned that Pluto was not the only object of its type. There were a lot of these other what we call trans-Neptunian objects, and objects that kind of live out in the Kuiper Belt beyond Neptune's orbit. We found a body named Eris that was about the same size as Pluto, and then one named Makemake, named after the god of the bird cult of Easter Island, which I think is a little bit smaller, but sort of in the same ballpark. And it was discovered around that time as well. And then finally, when we had probes take pictures of Pluto, they discovered frozen methane, carbon monoxide, and nitrogen. And none of the planets, not even the gas giants or ice giants or whatever, have this kind of composition. So it's not made from the same stuff. Its orbit is like crazy goofy, and it's not even unique, right? It's definitely not the dominant gravitational feature. And for all of these reasons, as quoted on Rick and Morty, it was demoted from planetary status in 2006 by the International Astronomical Union. So Pluto is actually a Kuiper Belt object, and objects like it that come inside Neptune's orbit are called trans-Neptunian objects. The Kuiper Belt, of course, stretches from about 35 astronomical units to about 50 or so, inside the Oort cloud, but outside of Neptune's orbit at about 20 astronomical units. Outside of that, of course, is a region where rocky particles exist, but not like in a disk, like in the rest of the solar system. All of the Kuiper Belt and the asteroid belt, all the planets are all kind of like in a disk, where the old accretion disk around the sun used to be back, when it was like a protostar and all that. And this is where comets live, right, in this place that's outside of the Kuiper Belt. And it's more spherical, right? It kind of envelops the entirety of the solar system, kind of in all directions. This is where comets live, and unless they're actually traveling to the inner parts of the solar system, they spend most of their time out there in this place we call the Oort cloud, O-O-R-T. And if you look at the diagram, the cross-section, it kind of looks like a lot, but if you add up all of the mass of all the comets, there's like 1 trillion or something out there. There's a lot of them, right? If you add up the mass of all those comets, it's about half the mass of Jupiter, so maybe not as much as you might think, but still kind of a lot. In any case, it may extend out to about 50,000 AUs, or about 1 light year, and that's kind of where the sun's gravitational influence ends. At that point, the force of gravity from the sun is so weak that it can't move like a hydrogen atom or a dust particle or whatever. Comets are icy. If you remember, we called these objects, these larger objects, more massive ones made from chunks of other material that have banged into other chunks of material and made all larger objects. We called them planetesimals. And the planetesimals that are way out there in the Oort cloud are commonly made up of dust, but also lots and lots of ice. Now, because they're so far from the sun, when stars pass near, within a few light years or so, depending on their mass, they can perturb one of these objects to sort of falling into the inner solar system, in which case they make like an orbit. Like Halley's Comet comes around to the inner solar system once every 76 or so years. And when it does, when one of these comets does come into the inner solar system, it kind of makes a spectacular presence, right? It has a spectacular sort of appearance in the sky. And if you look very, very closely at a comet, what you'll see is they kind of have two tails. One of them is a tail of dust, and that's just, dust particles falling off of the comet as parts of it kind of melt and heat up from the sunlight. And as it does so, it kind of leaves this dust trail where it's been, right? Just like a trail behind where it's gone. But also, there's a second tail that points away from the sun. Because as the sun's heat hits it, right, when the solar wind hits it and sunlight hits it, it ionizes some of the ice, and that blows some of the particles away from the sun. And so you often have two tails that are kind of pointed. One is, in the direction that the comet has been, and one is like away from the sun. So they're not usually pointed in the same direction. At least not for very long, depending on, where the comet is actually moving. But comets are not the only icy fields of material in our solar system. One need look no farther than the outer planets, the giant planets, to see that they all have rings. And if you remember, when something like a comet, an icy planetesimal, or a big chunk of icy rock, whatever, or just a chunk of rock in some cases, hits the Roche limit such that the tidal forces are greater than the force of gravity, the object gets shredded, and the material kind of spreads out over one gravitational zone around a planet and makes a ring. And that's the going theory as to why things get made. Either that, or it's possible that they never actually got to form a moon, never got to make a moon because of their proximity to a planet and another moon. Well, I'm not sure which one it is because I wasn't there. And so none of us are really quite sure, but that's our guess. Now, the book doesn't really mention Jupiter's rings, but they do exist. It is worth noting that they are there. They're not shiny and bright like Saturn's rings. Saturn's rings, of course, have lots of ices and materials that reflect a lot of light, but Jupiter's rings do exist. Saturn's rings were spotted in 1610 via telescope, and Jupiter's rings, because they're not as dense, they don't reflect light as much, and so on, were not seen until the Voyager 1 probe passed by Jupiter in 1979. So we haven't known that long that they were there, but they're there. There are essentially two outer rings called the Gossamer rings, and there's one main wide ring. And then there's an inner ring that's not flat like the other ones. It's kind of like a donut, kind of like a toroid. We call that the halo. Saturn, of course, has the most impressive ring features of any planet in our solar system. And the brightest of these rings going inward from the outside are called the A, B, and C ring. Most of the rings of Saturn are in the B ring. There are also the E and F rings. The E ring is associated with the moon Enceladus. And if you remember, that's the one where all of the water and the ice are. So guess what the E ring is mostly made out of? Yeah, water, ice, right? So the E ring is kept ribbon thin by its two shepherd moons, Prometheus and Pandora. And Prometheus, of course, is the Titan who stole the secret of fire from the gods, and so he was punished by being banished to an eternity in Hades, right? And Pandora was the first human woman created by the gods as part of humanity's punishment. It's likely that this thing that we all call Pandora's box is actually a bad translation, and that she actually had a jar. And she opens the jar that was given to her by the gods and unleashes evil and plagues and pestilence and all this stuff, famine and war and whatever, onto the world. And when she closed the box, or the jar, the only thing that remained in it was hope. And so astronomers like to make all these kind of goofy references and kind of, I don't want to say inside jokes because, they're not like hidden or whatever, but because the E-ring is made up of water, ice, and we as human beings require water, ice, right? We require water anyway, right? As we'll see towards the end of the semester, the the only way that life, as we know it, for it to exist, is if you have carbon atoms that kind of link up on to each other, and that requires liquid water as a solvent. Not to mention, we have to drink water to survive, right? Speaking of which. And so, kind of the unspoken joke is that the E-ring is like human destiny because there's water there, and Prometheus and Pandora are supposed to be like our stewards, and that's why they're supposed to be the stewards of the fate, the destiny of the human race, right? They brought us fire and unleashed all this stuff onto the earth, and so those are our shepherd moons. Goofy, right? In any case, Uranus and Neptune, of course, also have rings. Uranus, the rings of Uranus were discovered when the rings occulted a star. When we were looking at Uranus in a telescope in 1977, we saw that the star dimmed a bunch of times. And the star did not go directly behind the planet, and so we knew that there had to be a bunch of rings there for the star's brightness to dim a bunch of times. Neptune actually has rings as well, and they're really, really faint and hard to see, and they're not as bright and shiny or fun and significant as Neptune's rings are. But they do exist, and thus we can conclude that all of the planets in the outer solar system do in fact have ring systems, as well as tons and tons of moons. And that's about it for our solar system. We've covered now the inner planets, the outer planets, the rings and moon systems, the Kuiper Belt, and the Oort cloud. That's basically our solar system, with the sun, of course, in the middle. Sol, the solar system. Okay, that'll do it for Chapter 9. If you have any questions, of course, get a hold of me through the normal channels. And I hope you have enjoyed today's lecture as much as I have giving it. I'll see you next time.